Can nanobots help us live forever? For the first time in human history, we're living with a growing elderly population. And compared to the technology that could await us in the next 100 years, we haven't even seen the half of it. After all, we talk about our 80-year life expectancy as if people born today will only live to the 22nd century, while ignoring any aging breakthroughs that could happen within their lifetimes. The biotech revolution of the past decade is leading the charge, with bioengineers turning life into a programmable medium, and biologists manipulating our genes and cells. But what if we could go even smaller, to the level of individual atoms? Many chemists and nanoengineers are seriously entertaining the idea of creating machines out of molecules. Nanotechnology is the field of science that works at the nanoscale, 1/1000th of a meter. But how can we possibly build mechanical parts at this small of a scale? It might sound crazy to believe, but you don't have to, because molecules themselves are the mechanical parts. To work at a tiny scale, the robots of the future will need tiny batteries, tiny cameras, and of course, tiny motors. Futurist Ray Kurzweil, director of engineering at Google, has been quoted saying that in just 3 decades, humans will have tiny robots that perform the same jobs as our blood cells, and they will do it 1,000 times more efficiently. Our future machines could very well be smaller than a grain of sand, or dare I say it, even smaller. Because our understanding of genes and computer technology is accelerating at an incredible rate, Kurzweil predicts that in just 25 years, the computer in your phone right now will be hundreds of times more powerful, while only being the size of a single cell, about 6 to 8 microns. The Foresight Institute has even offered a $250,000 prize called the Feynman Grand Prize to anyone who can build a nanoscale robotic arm with a nanoscale computer. Why not have tiny machines no bigger than a red blood cell that you could ingest or inject? Swarms of tiny chemical-based robots whizzing through your body, destroying pathogens, purging cancer cells, and cleaning out your arteries. This idea is called a nanobot. You might have heard people saying that nanobots don't exist, but what they're actually referring to is nanoreplicators, which, unless you count the ribosome, definitely don't exist yet. You might also hear people say that nanotechnology in general is just science fiction. And this is certainly true for what we call bottom-up nanotechnology, where ultra-small machines produce large objects. However, top-down nanotechnology, where large objects produce ultra-small machines, is in fact very real. To avoid confusion, it would be more helpful to think of nanobots as molecular machines, rather than artificial intelligence, as they appear in the Terminator franchise. The so-called nanobots we have today could potentially repair our cells at the smallest possible scale, rendering traditional biotechnology obsolete and making aging irrelevant. Right now, nanobots can be built 1,000,000 times thinner than a human hair, some just 2 nanometers across. Since the idea of a nanomachine usually evokes constructs no larger than a micron, nanobots will be invisible to the human eye and can only be created by stringing together molecules at the atomic scale. Their movement induced by enzymatic engines or tumor-seeking proteins. So, how is all this actually useful in life extension? Well, for example, when these chemical machines attach themselves to, say, individual cancer cells, then a laser beam can be fired through the skin to heat up the nanobots and create a chain reaction that destroys every tumor in the body. These little machines could be extrapolated to repairing things all the way down at the molecular level. And while flooding the body with millions of tiny machines does sound scary, it will be required to perform operations that a doctor can't. Back in 2004, scientists at New York University created the first true prototype of what you could technically call a nanobot. Their molecular machine bipedally walked on legs 10 nanometers long, powered with a chemical called psoralen. It can jog along strands of DNA, kind of like a conveyor belt, and from then on, the topic garnered public interest. In 2012, as the biotech revolution was just beginning, scientists began building the first nanobots that are made to look and act like DNA, so that they'd be ignored by the immune system while smuggling anti-cancer enzymes. Unlike chemotherapy, which harms significant amounts of healthy tissue as well, nanotechnology allows us to attack cancer cell by cell, arming nanobots with potent poisons and tagging them with proteins that match only to cancer cell receptors. Unlike the microbots we discussed earlier, You don't have to swallow them, because nanobots are small enough to be injected into the circulatory system, where they would swim around your blood vessels and break up potential blood clots or plaques. There's just one little problem. How would we get them to move around? Researchers from ETH Zurich came up with the idea of using external magnets to solve the problem of steering, but still needed a motor to move the nanobot through the blood. At the macro scale, a motor is created when a magnetic device spins inside a tube of electrical wire, the current generating a magnetic flux. But at the nano level, there's no way that could work. You can't just solder a wire into molecular complexes that run electricity. Instead, you need to take advantage of what's called van der Waals interaction to spin the rotor with atomic forces. To do this, engineers in China and Australia created a double-walled carbon nanotube motor by rolling two graphene sheets into tiny tubes, one inside the other, messing with the length of the outer tube to change the speed. Unfortunately, temperature seems to be a big obstacle in getting a nanomotor to work. But researchers from Singapore created a new kind of nanomotor using a tiny laser to expand elastic graphene into a piston for pumping chlorine and fluorine gas, almost as it would in an internal combustion engine. In another study, researchers at the University of Munich even produced a frictionless nanopropeller out of a single hexagonal molecule containing a silver nanoparticle rotating inside it. Normal macro motors are very inefficient because of air friction, but nanoscale motors, like the motor proteins that direct our muscle movements, deal purely with chemical energy and are not subject to air friction. Granted, nanobots using all these devices would move pretty slowly, but researchers might just be able to supplement these motors with a high-speed, remote-controlled nanorocket complex. A nanorocket is essentially a pyrostyrene bead covered in gold and chromium, attached to a catalytic engine made of DNA. When it reacts with hydrogen peroxide, the engine can be propelled through bodily fluids on bubbles of oxygen. With these kinds of mechanisms, researchers have finally gotten serious about developing medical nanobots. Not the highly intelligent metal nanites from sci-fi, but simple, non-thinking chemical machines that can heal us in ways our natural biology never could. To differentiate them from over-exaggerated nanobots you see in movies, philosopher Anders Sandberg has instead suggested that we call them TECHNOCYTES, defined as any nanoscale artificial device in the bloodstream used for repairs, cancer protection, or as an artificial immune system. These technocytes aren't as complex as an actual robot, and can be made very efficiently from stages of self-assembled particles. Technocytes also include the idea of respirocytes, where we could one day hope to develop millions of tiny nanites in the blood vessels that could release oxygen and take up the carbon dioxide more efficiently than hemoglobin. Respirocytes could let us breathe longer in hostile environments, like underwater or on Mars. These technocytes could one day perform the entire functions of specific cells, making them obsolete. Perhaps we could even have nanoribosomes, allowing our body to make millions of new proteins that we couldn't previously. Nanolysosomes that break down the junk inside our cells and keep us healthy. Similarly, Ken Clemens gives us the idea of nanochondria, human-manufactured nanomachines that we implant inside living cells to produce energy more efficiently than our natural mitochondria. You can see where I'm going with this. The end goal of nanobots would be a kind of transhumanism, where every cell is replaced at the molecular level, until machines are all that remain. Of course, this is a long ways off, but the journey of 1,000 miles begins with a single nanometer. To achieve these feats of cellular bionics, new kinds of technocytes are leading the charge. Namely, nanosubmarines, the famous Voldemars, and of course, nanobees. First, we have nanosubmarines, Fantastic Voyage style. The idea of nanobots patrolling our bloodstream and looking for rogue cells was inspired by the body's own immune system, specifically, our white blood cells. In a recent study, researchers have developed a new kind of nanobot that could replace these white blood cells, and it works by propelling itself through our bloodstream with a nano-engine and self-destructing inside cancer cells. The researchers accomplished this by assembling a synthetic nanoscale vesicle, filling it with anti-cancer drugs, attaching it to a molecular motor, and tagging it with markers that guide it towards tumor cells. While drug delivery systems have been developed before, this new vesicle could be a more accurate and more efficient propelling device, since it's powered by a chemical nanomotor. The nanomotor uses hydrogen peroxide for fuel, degrading it to propel itself forward until it's eaten by the cancer cell. After the vesicle passes through the cell wall, a compound found only inside cancer cells called glutathione triggers the nanobot complex, prompting it to self-destruct and release a payload of chemotherapy molecules inside. Glutathione reacts with disulfide bonds of the nanomotor in such a way that it delivers the cancer drugs, kind of like a Trojan horse. However, since healthy cells have negligible levels of glutathione, mostly the cancer cells will get hurt, and damage to healthy cells will be minimized. But how can we improve the efficiency of such a device? Currently, the main problem with curing cancer is that drugs injected into the patient are not only killing rogue cancerous cells, but healthy cells as well, even if it is in very minimal amounts. But what if we could program a tiny molecular machine to carry them only towards cancer cells and nothing else? DNA origami is a technique that allows scientists to use DNA molecules as programmable building blocks that assemble themselves into designed structures. By taking a single strand of DNA, scientists are able to manipulate the genetic code and program the DNA to self-assemble into predetermined shapes. Complex artificial molecules called foldimers are very much like molecular Lego pieces, with complex bumps and hollows defining precise patterns of interconnection. Today, researchers at Caltech, led by Dr. Ido Bachelet, have managed to transform these self-assembling structures into drug delivery machines that kill no healthy cells. In a recent study, they manufactured a box-like scaffolding, shaped like a hexagonal tube, with the intent of smuggling antibiotics and chemotherapy drugs. The cage was composed of two halves, connected by a latched hinge, as well as a controllable lid that swings open like a clam whenever it biochemically recognizes target cells. Think of it like a lock and key, where only cancerous cells have the specifically shaped protein keys that could open the nanobot. When the researchers released these foldimers into a mixture of healthy and cancerous blood cells, half of the cancer cells were destroyed in 3 days, with literally none of the healthy cells harmed. In another study, the scientists tagged these nanobots with fluorescent proteins, monitored them with tracking systems, and injected them into live cockroaches, where they recognized target cells with flawless precision. The best part is that after they've done their job, we can release specific enzymes into the patient that gradually degrade and dismantle the nanobots, releasing them in non-lethal doses until the remains can be excreted out of your kidneys. Unlike previous nanobots, foldimers are naturally biocompatible and biodegradable, being specifically designed to bypass the human immune system that would otherwise interfere with the medication. Bachelet demonstrated how we could attach molecular markers to these foldimers, corresponding to the proteins on only sick cells, so that no healthy cells will let them inside. Upon publishing these findings in the journal Nature Nanotechnology, researchers designed a 3-piece nanobot to create foldimers that move and even sort molecular cargo. Composed of a tail to move, an arm to carry the cargo, and a molecular trigger molecule that releases the cargo. They measured its ability to sort things using fluorescent yellow and fluorescent pink dye molecules, allowing them to visibly see how well the machine delivers cargo to a designated location, with about an 80% chance of accurately delivering it. Scientists from Arizona State University and China's National Center for Nanoscience and Technology expanded on this idea with foldimers that carry the blood clotting enzyme, thrombin. Using thrombin as their cargo, these nanobots would block the blood supply of tumors and suffocate cancer within 24 hours of treatment. A payload on each bot's surface called a DNA apatamer directed it towards nucleolin, which is only generated in large amounts on the surface of tumor endothelial cells, meaning that these foldimers can locate cancer cells inside mice and pigs without any help from the scientists. In a recent announcement, Dr. Bachelet disclosed that nanobots are no longer science fiction and are currently capable of identifying 12 different kinds of human cancer cells. His team has now moved on to human testing in an attempt to remove cancer from individual patients. Unfortunately, foldimers do have one simple weakness. Programmable DNA is somewhat expensive to synthesize right now, so is there a cheaper way to end the looming threat of cancer? Cardiologist Samuel Wickline at Washington University School of Medicine has invented a self-assembling nanoparticle that might just be able to do the job more cheaply. The machine is smaller than a virus, but travels in groups of billions. They're called nanobees, designed to travel through the bloodstream, find cancer cells, and inject them with bee venom, which is harmless on a large scale, but toxic to individual cells. The nanobee keeps its venom inside a sphere of carbon and fluorine atoms, about 300 nanometers in diameter, letting it safely carry the toxin through the body without harming a single healthy cell. The melittin toxin is stored in an outer fatty layer designed only to release the venom when it selectively locks onto proteins linked to cancer cells. With that said, I think the chances of FDA approval are looking pretty good. In the words of Dr. Wickline, just as a real bee, the nanobee can only sting once, so swarms of them will be required for any treatment. We can manufacture these swarms cheaply because they're calculated to self-assemble without complicated machinery or expensive DNA fragments. Just put the right material together in the right container at the right temperature, and they will make themselves. Overall, technocytes like nanobees, nanosubmarines, and foldimers are truly a paradigm-shifting way for specialists to approach medical problems. But what do all these strange machines mean for our daily lives in general? In addition to clearing out arteries and hunting down cancer cells, we could theoretically invent a nanobot for every ailment that plagues humanity. What about nanobots that are triggered by blood sugar levels to pick up and release insulin for diabetes patients? How about nanobots swallowed in a pill that instantly hunt down well-known viruses, a feat that our adaptive white blood cells take hours to do? What about blood clotting nanobots that hide inside your blood and instantly stop the bleeding seconds after a car accident or gunshot? How about respiratory nanobots injected into victims of drowning, where they would break down the excess carbon dioxide molecules and carry oxygen to the blood or tissues? I also probably wouldn't mind using them to go scuba diving for a few hours without needing a mask. Technocytes could mean the very difference between life and death, and in the future, we're not going to have routine doctor's visits like we do today, but rather install systems in our bodies that continuously monitor our biology, detect problems, and fix them without us even knowing. The customizability and specialization of these machines could promise humans virtual invincibility, not just from aging or senescence, but from every possible form of death altogether. To quote late Nobel Prize-winning physicist Richard Feynman, who was credited with starting the nanotechnology movement, it would be interesting in surgery if one could swallow the surgeon. Ray Kurzweil's prediction of technocytes granting us immortality by 2045 still seems far-fetched to most people. I agree that the time frame seems a little crazy, but when you take into account how much more efficiently we can do things at the nanoscale, there's no limit to the diseases we can treat. But it doesn't stop there, because nanotechnology won't just give us longer lives, but better lives. Lives that are richer and fuller. If it's super strength you want, then it's more a matter of creating nanomachines with light-activated sliding sheets that create synthetic muscle. If it's morphological freedom you want, then we could have nanobots that rewrite the individual bases of our DNA. If you want to sleep for 1,000 years, nanobots could potentially carry tiny doses of cryoprotectants, like DMSO, to prepare our tissues for cryonic freeze preservation. And when being thawed out, deliver nanomagnets that gradually heat up our tissues cell by cell. Once we've replaced most of the cells in the human body with artificial cells, maybe we could also replace our neurons with nanobots as well. In the transhumanist perspective, nanobots are also seen as the sole escape route from our tragic meat machines, because they could locate each and every one of our brain cells and potentially send back data from them to an external computer. Gradually transferring neural functions like memory to nanobots would technically be a form of mind uploading, letting you constantly create backups of your personality inside an international distributed computer network. It would be kind of like save states in a video game. If you die from a car crash, you can just download your last personality backup, upload into a new body, and pick up right where you left off. Posthumanists have theorized that if we create a map for the complex web of connections in the human brain, then with enough resolution, these nanobots could store software copies of our consciousness, freely flowing through the cloud, and completing the final step towards the merger of man and machine, where our souls would live forever in a digital heaven. If this ever happens, it would extend our mental capabilities to such an extent that we will be able to write books within minutes, read each other's minds, and even combine our identity with super-intelligent AI. The current potential for nanotech is limitless, and many scientists agree that at our current rate of technological development, it won't be long before nanobots are customized to treat every kind of cancer or viral infection. It seems that our best hope for immortality might not come from large machines, but from small machines. Machines that are smaller than a speck of dust, but larger than life.